Earlier in the week, what was that line? We have a research sphere.
Oh, yeah.
Let's not do the math here. I'll include a problem like this in the comments underneath the video. But let's say we have a research sphere, and it is submerged in a lake, and it's 10 meters off the bottom of the lake. Agreed? The question is, what is the tension in the line that's going to keep it at that point? Completely submerged, but off the bottom of the lake. Can we picture this?
Yes.
Do you know whether the line is down or up?
No.
Not yet, because that line could just as easily be attached to a boat as it could be attached to the dirt. Agreed? It could be an anchor line, or it could be, what do they call those lines? I don't know. But a line attached that keeps the thing from sinking. And what's the only way we're going to know which way this thing is going? Mark, you're up. What's the only way we're going to know whether this thing is sinking or rising?
The veg.
Veg?
Well,
if it's sinking, what's got to be the greater?
MG.
If it's sinking, mg's got to be greater than veg. If it's rising, veg has to be greater than mg. So if veg is greater, is the tension to the base of the lake or the boat on top?
The boat on top.
If veg is greater, it's rising, therefore we need tension down here. If mg is greater, then it's sinking, and we need a line attached to the dock or the boat up top. Agreed?
Yep.
All right, there'll be a problem like this in the bottom of this video, so take a look at that. But that's a nice problem. If you understand that, you understand Archimedes. All right, questions?
So if you're saying if MG is greater, you need tension going up.
If mg is greater, Paige, this thing is sinking like a rock. Therefore, you need a rope attached to the boat or the dock on the surface. If veg is greater, this thing's rising like a hot air balloon. Therefore, you need tension anchored to the base of the lake, to the bottom of the lake.
Correct.
So finding that tension, if you can do that, you understand Archimedes. Because there's a lot there. Let's look more closely at this Archimedes problem. We have a volume of aluminum held under water, fresh water. It would sink to the bottom because its density is so high, except for the fact that there's a tension line holding it submerged without falling to the bottom. The mass of the aluminum, 25 grams, is equivalent to 0.025 kilograms. Given the density is 2,700 kilograms per meter cubed, we can find the volume using volume equals mass over density. That gives us a volume of 9.26 times 10 to the minus 6 meters cubed. It's a static condition, therefore forces up equal forces down. Therefore tension plus buoyant force has to equal the weight mg of the aluminum. Therefore tension equals mg minus buoyant force. Crunch the numbers, tension comes out to 0.154 newtons. Check below, there's some notes in the comment section that will explain. Okay, part 2. Pascal. This is a Pascal press. We got a small cylinder here, a big cylinder here. If I fill this with water, with no forces on left or right piston, where's the water going to go? It's going to be at equilibrium, right?
Yes.
I don't care what you put in there, this level will be the same as
Yes.
we see it every day, don't we? Okay? So, notice that these 4 tubes are all opened at the top. I don't care which tube you put red water into, they will all rise at the same rate and they will all maintain the same level horizontally. The question is, what force do I need there such that I can lift a 400 kilogram mass 10 centimeters? Okay? Let's say my radius, and these are perfect circles, let's call these perfect circles just to get the idea down. Radius 1 is 0.2 centimeters, radius 2 is 0.8 centimeters. Let's say I'm full of fresh water. I think that's all I need. So, we're applying a force here. Do I have to apply a 400 times 9.8, almost 4,000 Newton force to get that mass up?
Not at all.
No, I have to apply a much smaller force, and that's the guts of a Pascal press. Small force, small area, gives me a big force, big area. Agreed? This is like feeding in photo.
Yeah.
Where do we see feeding in photo, by the way?
Pulley and
In all simple machines, quite frankly. We've only looked with it with levers and pulleys. What's a sophisticated pulley called?
Block and
Block and tackle.
This fish something.
Where's fish and block?
tackle.
Oh,
It's like bait.
no, I still don't get
It's
it.
like bait. It's like tackle box. is
Like
where
bait,
you-
bait and tackle?
Well, tackle box is where you keep
A tag, all right, I'll give you that, tackle box.
tackle box.
All right, so how are we doing? What are we going to say first? The pressure here has to equal the pressure right here. Agreed? And pressure is equal to one of two things. And what are those two things?
F over A.
Force over area, and it's also equal to rho GH. So, what's my pressure at point 1? It's got to be F over the area of this cylinder.
Yes.
What is the pressure caused by right here at point 2?
F over
Over
A.
A
Plus.
plus rho G.
F2 over area 2, I'm going to call this F1, area 1, plus this column of fluid, yes?
Yes.
So that's got to be plus rho GH. And I'm going to solve for
F1.
F1. So give me the numbers here, F1 over
Pi
JC and Rakai, get these numbers as soon as we're ready.
over
Please.
pi times point.
The area of a perfect circle, pi r squared. So I'm thinking pi,
Times
Point 002.
we got to change that to meters, 0.02.
Two zeros.
That's your, Ray? Thank you. 0.02 squared. Pi r squared. Agreed? Has to equal, JC, what's the force on that 400 kilogram mass exerts down? How do we change masses to forces? mg, right? So 400 times 9.8, 3,920. What are the units? Newtons, thank you. Over the area, what's the area if the cylinder has a radius of 0.8 centimeters?
Pi times point 008.
0.008 squared. Plus
1,000.
fresh water, 1,000. Now there was some confusion about this. The density of water is 1,000 kilograms per meter cubed. What is that in the CGS system? That's MKS, CGS. What is it in the CGS system?
Is it 1?
1. What are the units?
1 gram per meter. Gram per
Centimeter.
inch.
What are the units of length in the CGS system?
Feet.
Centimeters cubed.
What is it?
So 1 gram meter cubed is equivalent to 1,000 kilograms per meter cubed. Okay?
Makes sense.
I know there was some confusion about that. So that's plus fresh water,
1,000.
1,000, earth sea level,
9.8.
9.8. What do we not like? 0.1. Are we good?
Yes, sir.
What force do we get?
245 newtons.
245 newtons. JC, agreed?
Yeah.
So the force has got to be 245 newtons. Is this a nice machine? Pushing down 245, and what are you getting out?
400.
Rock and roll.
3,000.
You're getting out to almost 4,000
My
newtons.
bad. 4,000.
Oh, shh.
Rock and roll.
Critical mistake, Jules.
You're right.
And I got it on video.
Yeah, someone said it first. I confused.
So that's 245 newtons down, and we're pushing up 3,900 newtons. That's a very, 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 very nice machine.
Is that an efficient machine?
Well, whether it's efficient or not, what is efficiency of a machine equal to? Efficiency equals
Work
Work over time.
what were we over what over we?
Work out
What over we?
over work in.
times 100. No, I think times
You don't have any distances here. That would be a little harder to figure out. It has a nice mechanical advantage. What's the mechanical advantage of this? Oh, so I got 23 puzzles last year. Mechanical advantage equals what over what? It's stamped on the side of every machine box.
Forces out.
Forces out over.
Forces in.
Forces in. So what's the mechanical advantage of this?
4,000.
4,000 over.
245.
That's a very high mechanical advantage.
You
Very-
also got that good answer
You
on
could
video.
you could sell a lot of these.
mistake.
Say it again.
Oh, wait, never mind.
Let's try to note
That-
it on my
Good answer. That's
This shows like 100.
All right.
I need to go back to bed.
Questions? Questions? We're good?
Yep.
Okay.
Wait, no, we
Let me just.
Wait, we should just the face and tell us looking at the face.
All right. I think that's it. All right. Very good. Thank you.
Face it after.